So in this video, we're going to look at an example of using linear discriminant analysis, and we're going to look again at the iris dataset. So if you remember, that was the dataset where we got measurements on 3 different species of iris, and we'd measured 4 different things about each one. But to begin with, to make it simpler for us to see what's happening, we're just going to look at a subset of the data. We're going to look at 2 species, the Setosa flowers and the Virginica flowers. And we're just going to look at 2 of the measurements, the sepal length and the sepal width. Now, if we plot the data here, this is 50 Setosa flowers and 50 Virginica flowers, we can see that they are quite clearly linearly separable. You could draw a line between these 2 data sets that would have a good prediction accuracy. So it looks like LDA, linear discriminant analysis, should work really well in these cases. So let's see if we can work through the calculations that we'd need. Well, first of all, we need to work out the sample means and the sample variances for each group. Okay, so I've done this here for you. And here's the sample mean for the Setosa flowers, and here's the sample covariance matrix for Setosa. Okay, and the same for the Virginica flowers. Now, if you remember, in linear discriminant analysis, we assume that the data have a shared covariance matrix. Okay, so here, if we look at these 2 covariance matrices, they are somewhat similar. Okay, but really quite, there's some differences as well, but they're close enough that we can probably try linear discriminant analysis and see what happens. In a moment, later on, we'll talk about letting them have different covariance matrices, but to begin with, let's find a single pooled covariance estimator for the data. So remember, the way we find a pooled covariance estimator is we add up the number of data points times one covariance matrix plus number of data points times the other covariance matrix, and that gives us, and then divide by the total number of data points minus number of groups, and that gives us our sigma hat here, which we find here. So this is our shared covariance matrix, our estimate of the noise on each for each population. We can then calculate the midpoint of the 2 means. So I've not plotted the 2 group means on here, but we can find the midpoint between them. And then we can also find the vector that goes from one population mean to the other population mean. Okay. So if you remember, what we're working towards finding is A transpose X minus H. So if we estimate A, that was sigma inverse times the vector from one mean to another. So if we work this out, we get this vector minus 10, 11.4. Okay. And I've given you some R commands here for working out the pooled covariance estimator, how I did it. Okay. But there is a command as well. If you install this library, there's a command that does a pooled covariance estimator. And once you've got a pooled covariance estimator, working out the other bit should be straightforward for you. So have a go at that. See if you can work out the means for each group, work out H and A, okay, and see if you can do this. So our sample maximum likelihood discriminator rule is going to allocate a new observation X to the Setosa population if and only if A transpose X minus H is bigger than 0. Okay. So if we draw this line on the data, so if we find the line where A transpose X minus H equals 0, that's the point where we flick from classifying the Setosa to Virginica. Okay. So if we draw that line on, if we work it out, that's going to be given by this equation here. Okay. And if we draw that on, we get a line in this position just here, which you can see does exactly like we think. It draws a line right between the 2 populations. Okay, so you can see here there's one point that's misclassified. Okay, so this Virginica flower down here is on the wrong side of this boundary, That's okay. We're not going to have a perfect classifier. And the statistics say this line is optimal here. Now, so let's suppose someone comes along with a new iris that has a sepal length of 5.8 and a sepal width 2.5. What we'll do is see where this is on our diagram here. So 5.8, 2.5, so that's like this black cross here. And then we just see which side of the decision boundary it's on. So it's on this side, and that's the Virginica side. So in this case, we would classify this new iris as Virginica. Okay, and if we work out what A transpose X minus H is for these data, we get -8. That's less than 0. So we classify as Virginica. Okay. Now, thankfully, we don't have to do these computations ourselves. There is, just as you'd expect, an R function to do this for us. And the R function we're going to use is this LDA command, and it's in the mass package. Okay, so before you use it, you always have to do library mass. Okay. And the command works in the same way the linear regression command works. Okay, so we can do, if we pass it the data frame here, so iris 3, I should have said, is where I've just selected Virginica and Setosa flowers. Okay, so I've excluded the versicolor ones. And I've just selected sepal length and sepal width. Okay, and I've stored that in a data frame called iris 3. Okay, so this LDA command says what is our class label, so that is species in this case, and what are the covariates, everything else. So I've done species twiddles dot here to mean all the other covariates, and so that is I given the data frame iris3, okay, and that gives me an object back. Another way of doing this, we could have said LDA is species twiddles sepal length plus sepal width. Okay. So just explicitly say what covariates to use in our linear classifier. Okay, and if we look at the output from this, it tells us what model we fit. Then the first thing it gives us is an estimate of the prior probabilities of the groups. Okay, so in the Bayes classifier, these are the pi k values. So in this case, we've got 2 species, so we've got 2 values for pi. Okay. And remember, we said we'd estimate them by the number of observations in that group divided by the total number of observations. But in this example, we've got 50 flowers of each type, 100 in total. So our estimate is going to be 50 over 100, a half. So in this case, we estimate both of these to be 1/2. Yeah, so 0.5, 0.5. Then it gives us the group means. So for Setosa and Virginica, they're the same as we computed before, I hope. Okay. Yeah. And then it gives us the coefficients of these linear It gives us these coefficients of these linear discriminants. Okay. So this is not exactly the same thing as we got. Okay, we found our values of A to be -10 and 11.4. Okay. Whereas here, we were given these coefficients. So where's it gone? Here, 2.2 and -2.5. So we're going to talk later about how we find these things in general. Okay. But notice that all that matters is their ratio here. Sorry. So if we look at the values we computed, -10.03 and 11.4, and look at their ratio, we get a ratio of -0.88. Now, if we look at the values given to us by R, so that was 2.2 divided by their ratio is -2.51, we get the same ratio, -0.88. And they're exactly the same if you do put more decimal points in here. Okay. So in other words, this vector we found, A, R has given us another vector that's in exactly the same direction. So they've got a different length for that vector because they do the calculation differently, more efficiently, okay? But it's that vector in the same direction, which is what matters for us. Okay. We can also make predictions here using R. So to predict, we use this predict command. We have to pass in our LDA fitted object. So that is called iris.lda1 here, because that's what I called it when I did the command up here, iris.lda1. And then I have to pass in the value of X I want to predict for. Then you have to pass that in as a data frame. So I've created a new data frame with the sepal length 5.8 and sepal width 2.5. So like we had in this figure, this point here. Okay, so I've created a data frame with the right column names on. So where's it gone? Yeah, with the right column names. And you just pass it into this predict command, and it passes us out the following. So first of all, it gives us the class label it's predicting. So in this case, it is predicting Virginica, which is exactly what we got, right? We said we predict Virginica here. It then gives a prediction of the linear discriminant score, but because we've got a different A to what they had, we get a different answer here. Okay, and they also give posterior probabilities for the iris belonging to each of these two classes. So we get a probability that the new iris is setosa and a probability it's Virginica. And the way these are computed is, again, using Bayes theorem. So we've got the probability that we're in class. So this is the calculation we had before. This is the probability that we are a type K given X. This is the same as we looked at in the theory that we had. Okay. So we have to plug in to the multivariate normal distributions here, the estimated mean and covariance function. But if you do that, you will get these numbers. Okay. So now let's use the entire data set. Remember, we've got three populations here: setosa, Virginica, and Vetosa. It's versicolor, isn't it? Versicolor. And we've got four measurements: sepal width and sepal length, and petal width and petal length. So here we just use the command LDA again, species twiddles dot, the iris data set. So use species as our class label. Use all the other variables as the predictors. Okay. Now, if we look at what we get here, we get the estimates of the prior probabilities for each group. So the groups are all equally balanced. So we get a third, a third, a third. We get the group means given to us. And then we're going to get two sets now of linear discriminants. Now, I'm going to delay talking about why we get two sets here and what these mean until the next chapter. Well, the next section, sorry, of this chapter, where we'll talk about Fisher's linear discriminant analysis, and we'll explain what these mean there. Okay. We'll also think better about how to visualize linear discriminant analysis once we've seen the material in that section. But in the meantime, we can use this KLAR package to visualize something about it. So there's a command in there that's useful called partymat. And what partymat does, if you specify the method to be the LDA method, okay, that gives us, it does LDA for each pair of variables. So here it's done LDA with sepal width and sepal length as our x's, LDA with petal length and sepal length, with petal length and sepal width, and so on. Okay, and because we've only got two covariates in these cases, we can visualize the decision boundaries. So here we've got three species of flower: setosa, versicolor, and Virginica. I've just relabeled versicolor as color here because it abbreviates the factor level by its first letter. So I had versicolor and Virginica, so I was getting two sets of V's. So I've just relabeled versicolor color here, so you get a C. So what this does then is LDA for each pair of variables, and it plots the decision boundaries for us. So this isn't the same thing as this, in that it's just done 2 variables. Here we've got 4 variables, but it does help us visualize something about the data set. It's hard to visualize hyperplanes in 4-dimensional space, so this is one thing we can do to help understand what the discriminant rule is doing. In the next section, we'll see a better way of doing this. So these here are linear decision boundaries. And we said we get linear decision boundaries if we use the same covariance matrix for each population. Okay. So if we have populations 1 up to G, okay, and if we have population K being multivariate normal, we said that if we choose the same covariance matrix for each population, we get a linear discriminant rule. But we don't have to choose the same covariance matrix. We can let the covariance matrix differ between the different populations. So if instead of what we did before, we now put a subscript K here on the covariance matrix, so it's different for each population, we get what is called quadratic discriminant analysis. We get a discriminant rule that looks like this. Okay, so it's the same as we had before, exactly the same. But now we can't ignore the term in the log likelihood that is the determinant. If I go back to the log likelihood, yeah, we get the determinant of sigma here. If this is different for each class, I can't ignore it. Yeah. So we get the same form of a discriminant rule, but because we've got a K on these sigmas, we don't get the cancellation that we had last time. Remember, for linear discriminant analysis, we could ignore the cross terms here. We could ignore the square terms, the terms that had X transposed sigma X in. We could ignore them in the optimization because they didn't have a population indicator K there. But now in quadratic discriminant analysis, it does depend upon K, and so we can no longer ignore it. Okay. So we're not going to talk about the details of how we do quadratic discriminant analysis, other than to say, this is the discriminant rule we use. Just maximize the posterior probability still, or the log likelihood if you're using the ML version. But to do this in R, it's dead simple. It's exactly the same as we had before. We just use the QDA command. Okay. Instead of LDA for linear discriminant analysis, we have QDA for quadratic discriminant analysis. And again, we can use this party-mat function to plot the decision boundary for pairs of variables. And you can see that what we get in this case are not linear decision regions, but quadratic discriminant regions. Okay, so we've got similar kind of classifications of all the points, but we've just now got quadratic discriminant errors. Okay, and just finally, how can we say which is better here? Quadratic discriminant analysis or linear discriminant analysis? How can we choose between different methods? How can we assess the accuracy? So one way to assess the accuracy that's commonly used in statistics and machine learning is to split your data into a test set and a training set. So here we've got 150 data points in total. So I'm going to take 2/3 of those data points and use them for training my linear discriminant rule. I'm going to take the other third for testing my linear discriminant rule. So what have I done here? I've randomly sampled from 1 to 150, 50 points. Okay. So if we do this, sample 150, size equals 50. Okay. I get 50 integers between 1 and 150, and they're going to be my index. So I'm just going to pick out the rows of the iris data set that are given by these indices. I'm going to call that my test data. I'm going to get my training data by having all the other data points. So if I do minus these integers, I get all the other columns, all the other rows, sorry, the ones I missed out. So what I do then is I train a linear discriminant analysis classifier using the training data set, a quadratic discriminant analysis classifier using the training set, and then I'm going to predict the test data using my two classifiers. So I predicted using LDA and predicted using QDA, using the test data. So that gives me a whole load of class labels. And I'm just going to compare when they're the same as the real labels. Okay, so I've looked at the predictions and asked, are they equal to the real class labels, the species class labels? And I've counted up how many times they're the same. And I've divided by the total number of points, 50. And then we get an accuracy of 0.98 or 98%. 98% of our predictions are correct using the LDA classifier. We can do the same with QDA. We also get a 98% accuracy. So exactly the same accuracy in this case. And we can look in more detail if you want. If you do this table command, you can look at the prediction labels and the true species labels, okay, and see how often we predict setosa when the label really is setosa, how often we predict versicolor when it really is versicolor, and so on. Okay, and you can see we've got one misclassified case here. There's one instance where the label really was Virginica, but we predicted versicolor. Okay, so this just allows us to see that. Okay. And in general, we do this kind of thing all the time, but sometimes we do something called cross-validation, where we do this split into test and training data sets many times. So instead of just doing it one time, we might make multiple splits into test and training data sets. But cross-validation is not a topic for this module. You've hopefully seen it in machine learning module or another module you can take.